This video for AP Statistics is a brief explanation of the central limit theorem. It's magical. You're welcome. Okay, so the central limit theorem. What is the central limit theorem? Well, if you are familiar at all with calculus, in calculus we have a fundamental theorem of calculus, and it basically is what a lot of things that we do in calculus hinge upon. Well, we have the same thing for statistics. The central limit theorem is basically the fundamental theorem of statistics. Why? Because it tells me two vital pieces of information. The first thing it tells me is that as my sample size increases in our sampling distribution, that sample distribution becomes more normal and it decreases in variability. In other words, it becomes more like this, right? Bell-shaped, unimodal, not a lot of spread going on here. That's what the central limit theorem tells me. In other words, it tells me that if my sample size is large enough, then my distribution will take on a normal shape, and I can therefore approximate using the normal curve. So that is why it is all magical and stuff. Now, something that people often get the central limit theorem mixed up with is the law of large numbers, which we discussed when we looked at probability. So the law of large numbers tells me that if I keep sampling over and over again, and I am drawing at random from my population, it tells me that as that value increases, my sample mean gets closer and closer to the true population mean. Meaning if I'm flipping a coin, for instance, okay? Dadgummit. Sorry, kids. Okay, if I flip a coin, oh, and now I can't spell. That's score. So if I flip a coin, well, let's say I flip a coin 10 times. The theoretical probability tells me that I should get 5 heads and 5 tails, right? Well, in actuality, if I flip a coin 10 times, is that necessarily going to happen? No, but if I do it enough, okay, as n increases, as I flip that coin 10,000 times, 100,000 times, guess what happens? Well, I get closer and closer to this idea of it evening out, of it getting to be to the theoretical, getting to grow to the theoretical probability of about half and half. So that is what the law of large numbers tells me. So because people get the CLT and the law of large numbers confused, that's why I am addressing this for you. So notice that the CLT focuses on shape and spread. As our sample size increases, our shape becomes more normal, and our spread or variability decreases. All right, law of large numbers focuses on the center. So the three big ideas when we're discussing a certain distribution, we talk about center, shape, and spread. Those are the things we focus on. Center has to do with law of large numbers, shape and spread, the central limit theorem. Okay, so the central limit theorem, what we use it for in quantitative data, it tells me that my sample size is large enough because CLT focuses on this idea that if my sample size is large enough, I'll take on a normal shape and my distribution will become less variable. So that last condition that we talk about in quantitative is a large enough sample. Usually, it's a good practice to say that if we have the sample of at least 30, then we say something like, with a sample size of whatever it is greater than 30. Let's say I have a sample size of 45. So I'd say with a sample size of 45, we can approximate normal because of the central limit theorem, or because of CLT. So something like that. And I'll word it better when I do some examples for you. But that is what we will rely on. Also keep in mind, as I stated in another video, you do not necessarily have to have a sample size of 30 or more if you are told that your initial distribution is given normal. So let me try to explain this idea of the central limit theorem in a little clearer terms for you. so that you can understand it a little bit better. So I have a website here, and we're going to do some practice with this in class. Let's say I'm sampling from a normal distribution, and I am taking a sample size of 2. So what that's going to do, you're going to see some animation here. Okay, so what happened was it took a sample size of 2 from the initial population, it averaged them together, and then it dropped that little blue rectangle there. So let's do it again. So sample size of 2, average it together, drop it down. And I could do this over and over again. All right, but that's going to take some time. So let's do 5 at a time. Okay, drop those. Let's do 10,000. Score. Look what happens. Normal shape, sample size of 2. No big deal. Okay, so I want you to notice what happens when I sample from a skewed distribution. And I want you to notice underneath here this red mark and this little tiny red mark under there, that is approximately your center of your data. So I want you to notice that for a skewed distribution, it is not right in the middle of the x-axis, it's in the middle of the data. So please be careful with that and pay attention to that. So I'm going to stick with my sample size of 2. I'm going to let it take 2, average them together, 2, average them together, 2, average them together, 2, average them together, over and over. Let's do 10,000. Well, I want you to notice that when I take 10,000 samples of size 2 here, I still have a skewed distribution, don't I? That is an indicator maybe the sample size isn't large enough because it's skewed. Let's take a sample size of 10. So let's do 5 of those. Let's do 10,000 of those. That looks a lot more normal shape. It's unimodal, it stacks up in the middle, it's less variable. Notice the center does not change, okay? It's pretty much centered in the same spot because the central limit theorem doesn't have anything to do with where that center lands. It has to do with shape and it has to do with variability. Okay, let's say I'm going to make a weird distribution, okay? Let's say I'm going to make something weird like that. Okay, so notice where my center is, that little red mark there, and I am going to take a sample size of 2. I'm going to take 10,000 of them. Okay, well, 10,000 samples of 2 mean that I have taken 2 and averaged it together 10,000 times. Notice how wonky that looks. All right, let's try a sample size of 5. Better, more normal. Let's look at a sample size of 10. Even more normal. So see, my sample size, when I'm taking it from a wonky distribution, something that's really skewed or kind of, bimodal or something weird like that, my sample size needs to be bigger so that I can use the normal curve because a larger sample size is going to produce more normality, less variability. I hope you've enjoyed this.